Alrighty guys, we're going to go ahead and get started with our magnetism notes part 2. Now let's take a look at magnets and their properties. What would happen if we broke a magnet in half? Well, when we break a magnet in half, we get more magnets. Each piece is now going to have its own north and south pole. So in other words, it's going to look something like this. So when we start with one magnet, we have a south and north pole. When we break it in half, each new magnet has a south and north pole. So this is a great little trick in case you and your friend are ever hanging out and you guys find a magnet, but there's only one magnet and there's two of you guys. You can just go ahead and break that magnet in half and give half to your friend and keep half for yourself. Although these magnets attract and repel each other, they do not have plus or minus poles. So the poles, again, are called north and south. They're not positive or negative poles. They're just north or south poles. Let's take a further look into creating a magnet. So let's think, how can we magnetize an object? If we want to make a strong magnet, well, we can go ahead and heat up a ferrous object. And if you remember from our last notes, a ferrous object is most likely iron, and let it cool in the presence of a magnetic field. When it's completely cooled, it will now be magnetized. For example, there's such things as ancient clay pots and lava, and we'll talk about that a little bit more on the next slide. And then if we want to make a weak magnet, we would let that ferrous object, again, ferrous object is just referring to iron, sit in the presence of a magnetic field. So how would this make a weak magnetic field? Well, if we had an object like iron, we know that iron is not generally magnetized, it's usually unmagnetized. And if we put it in the presence of a magnetic field, over time it would become magnetized. It wouldn't be a very strong magnet though, but it would be magnetized. And if we did what we set up here in order to make a strong magnet, if we took that and melted it down and then let it sit in a magnetic field, well, by melting it, we're exciting all of those electrons and we're able to organize them and make them spin in whatever way we want. And as it cools, they get stabilized in that way. So this is going to generate a very strong magnetic field, where if we just let a regular piece of iron sit in a magnetic field, it's going to change the spin of those electrons, but it's not going to generate a very strong magnet. So how could we make a compass? Well, a compass could be made if we took a bar magnet and we balanced it on a point. So this way we allow that bar magnet to spin freely. And what a lot of people will do is, you'll see over here, they'll take some water, they'll take a little surface and they'll put their bar magnet on this surface, allowing it to float in the water, which is allowing it to move around. We can see that this bar magnet over here and this compass are both pointed in the same direction. The unfortunate thing with this is that unless we know the poles of our bar magnet, we're not going to know which direction is north or which direction is south. So I talked about those ancient clay pots, and I want to talk about what we use the ancient clay pots for nowadays. Well, scientists have actually used these pots to collect data in order to chart the decline of the Earth's magnetic field. We talked about in the last notes how the Earth's magnetic field has changed over time, and it's going to change again. So now it's getting weaker and weaker until the point that it will finally flip poles like it did in the past. So does that mean that the world's going to end if the poles flip? No. If we use data from cool volcanic lava, we know that it reverses about every 200,000 years, which means that it's done it before, like we mentioned in our last notes. And because it's done it before and the Earth is still here, we know that we'll be fine. But as you can see, it looks pretty crazy up here. So as the Earth is getting between these reversals, which is where we are now, there's a clear north and south pole. But as the reversal begins to take place, these north and south poles start getting switched, which means that it's going to impact certain things in regards to the magnetic field. The last reversal, like I mentioned before, was 780,000 years ago. So we are due for another reversal, just not during our lifetimes. Now that we've talked about how to create a magnet, we need to talk about how to destroy a magnet. Because what if it becomes like evil one day and wants to take over the world? We need a way to destroy it. Well, what does it mean to demagnetize something? To demagnetize something, it just means that we are making those electrons of those domains spin in random directions. Because we know that randomly spinning electrons within domains does not generate a magnetic field. In other words, by taking those electrons that are spinning and making them spin in an unorganized fashion, we can demagnetize that magnet. Over here in our diagram, we've seen this before. This is unmagnetized iron, and this is a magnetic piece of material, or magnetized iron. In the magnetized iron, the domains and the electrons are all pointed in the same direction. In a demagnetized or unmagnetized iron, we can see that these domains and electrons are pointed in different directions. So how can we do this? Well, there's three very easy things that we can do. Number one is we can influence it by an outside magnet. So for instance, if we had a positive magnet here, we could influence it by putting another positive magnet towards it. By doing that, it would push these arrows into the other direction. We could hit it with an object or drop it repeatedly. Whenever we hit or drop a magnet, these domains become more and more disorganized. These arrows are going to point less and less in the same direction. The more we drop it and the more we hit it. Lastly, we could just heat it up. If we heat up this magnet, these electrons are going to get excited, which means that they're going to move around a lot more, which means that they're no longer all going to spin in the same direction. Let's talk about electric current, because we can't talk about magnets without talking about electric current. So how does electric current relate to magnetism? When electric current flows through a wire, it generates a looping magnetic field around that wire. If we take a look at our diagram right here, we can see that this green thing is a wire. So as that current flows from, let's just say, this positive side to the negative side down here, a magnetic field is generated around this wire. So if you take a magnet and put it next to a wire, you're going to notice that it's not going to be attracted to it. But if you plug that wire or that cord into the wall and then into your appliance and then take a magnet, you're going to notice that it is attracted to it. And the reason is that when we take current, like we said before, pump it through a wire, it generates a magnetic field around that wire. So what would happen to a compass that is placed on a wire with current flowing through it? Well, what does a compass do? A compass points towards the magnetic pole of the Earth. So, in other words, a compass is a magnet, which is influenced by a magnetic field. If we put a compass on top of this wire, it's going to be influenced by the magnetic field of the wire. So we should see, like we said before, that it would be influenced by the magnetic field, and it would no longer point towards the northern magnetic field of the Earth. And this is because the strength of a magnetic field is dependent on distance as well, and the distance from the Earth's magnetic north pole to our compass is pretty far away, but the distance from the wire to the compass, if it's right on top of it, is extremely close. Therefore, that wire is going to have a bigger impact on our compass, and it's going to override the magnetic field of the Earth. This is important because sometimes if you're ever out in nature, or maybe you've watched a movie where people are out in nature and they use a compass, and they are getting a weird reading from it, most of the time that happens when they are next to power lines. And power lines carry a lot of current. So because power lines carry so much current, they're generating these huge magnetic fields, which means that the power line is going to mess up any compass reading. So remember that next time you're lost in the wilderness and all you have is your compass, don't stand near any power lines as you try to figure out where north is.